Huh?
EM must be out.
No, I don't want to fade out. You're right, but I don't want to fade out. Isn't it E-R-E-A-I-I? Right? It passed here, right? We had this power here. There is some loss to come to the machine, right? Now we are electrical. It's going to be E-A-I-A, right? So what is next? Core loss. What is next? Here when I said P rotational, P brush is also is included, when you have or yeah. Now the next is going to be armature loss. R-I-I-A squared plus dBi, right? This is in the armature circuit, right? Ohmic loss in the circuit, right? Now, what is this? What is this now? If it is self-exciting machine, let me say this is a PR. But there is one thing I should say here. See, excitation system also has a loss, right? I'm going to put it this way. P RFIF. Here I don't connect it here because it's not coming from this source, right? It's coming from an electrical source, a separate source. But I didn't connect it over there to that line, but there is another loss, keep in mind, in the system, right?
I was just going to ask what the variables were for after EAI.
This one, the bottom one is the P core loss, and this one is the armature loss, ohmic armature loss. And this one should be 2 times 2. RAIA squared plus 2 VBIA, right? And we have a excitation loss. Because I put it here. It could come for the only one doesn't connect here is this excitation. For the series, for the shunt, for the compound we're going to talk about, all of them is going to be connected here. That one also is coming from here. But for this one, because it has a separate source, I cannot put it in this power chart. And the output is VTIA, right? That's the output power. P out is the VTIA. Now, how about if you have a motor? What's going to happen? Motor is going to be like this. What is the input power? E in is going to be VTIA, right? That's the power coming to the motor, right? What is the first loss? Armature loss, all right? What is next? See, if you look at it, the power is coming here. You have armature loss, right? From armature loss, we are going to go to the machine, right? See, from the stator, we are going to the rotor, right? If you look at it, it's like this. See, just let me put another one here. This is the rotor, and this is the stator, right? This one is connected here to the VT, right? The power is coming here. We have some loss RAIA square VT. We come to this core. Doesn't matter really which one comes first or second, but just I'm going with this order. We're going to have some iron loss here and some iron loss here, right? No. I'm saying we have some iron loss here and some iron loss here. Yes or no? Only in the middle. Because here is DC, right? There is no iron loss or core loss. Core loss, keep in mind, frequency. If the frequency is 0, there is no core loss, right? Here is the DC, right? Here is the AC. electrical power coming here, some resistive and brushes loss come inside here, we have some core loss. Now, this one is gonna go out, right? It's gonna go to the shaft, right? So basically we are gonna have the armature loss, core loss, and what is here? They call it, sometimes they call it developed torque and those kind of things. But this one is going to be basically EA, IA, right? So after here, what we are going to have? P rotational, right? We are going to, when it's going to go to the shaft, we have a bearing, I don't know, windage, you know, all those kind of losses. And here is going to be P out. How much is the P out? PM times omega.
And where would your excitation losses fit?
Oh, excitation loss, as I said, because it's not coming from this system, again, we can put it kind of parallel here. Say RF, IF square. But here I cannot, because this is a different source, you know, I cannot put it on this tree, you know. Just I'm saying there is something like this. But it's not coming from this source. Right? When we go to the shunt, you know, you can see I can say that, you know, very fast. So this is a power efficiency, this is a power tree for the either motor or generator. You can see how the power is going to go through the machine. Now let's go to the shunt excitation. I really would like to talk about the commutator and what kind of thing, but I think Sunday, the same class here, hopefully they say it's going to be open. Sunday, 9:30 will be here. I'll bring maybe a few slides about the commutator and the armature reaction, you know, maybe 10 minutes I'll talk about that one, you know. And because I really would like to tell you what are those things. It's very difficult to put it on the board and we don't have very much of time to go through the details, you know. I need to finish the DC machine before I leave. So it will be good for the lab, you know, for the first 4 labs. I think the lab they're going to start from next week, right? We're going to be the first lab. Now shunt excitation. Shunt or self, they call it self excitation. Or shunt. I'll tell you why they call it self and they call it why they call it shunt. In this case, let's go back to the generator. Generator. Basically, when we are solving the problem, usually we don't put the LA in the circle. Why? Because the voltage drop across this one, SDS stage is how much? 0. Some books you see they don't put even LA, they just put R value. So this is what we know from a generator. But they call it self-excitation. Self means that one was separately excited. Means there was, we said means there is a separate source to power up the excitation winder, right? But here is the self-excitation. The reason they call it self, because the excitation winding is supported by its own voltage. There is no extra source to support this one. They call it self-excitation. They call it shunt, because look at here, This one is parallel with the armature circuit. This is the armature circuit, right? This one is in parallel with the armature circuit. They call it shunt. Shunt excitation or self-excitation. So let's look at this one, how it's going to work. I'm not sure. When I was a student, we had this for this test in the lab, but I'm not sure we're going to have it here or now. Let's write the equation first quickly. The equation is pretty simple here. We said again, because this is generator, I'm going to put it this way, is the EA minus U through VBIA minus RAIA, right? This is the output voltage. The IF is equal to VT over RF plus RFX, and P out is VT IL, which IL is IA plus IF. These are electrical equations for the shunt machine, and you can see it from the circuit. It's very simple. You can write those.
Wouldn't it be minus IR?
Now, I'm going to talk about the interesting part. Yes.
When VT times IA on the VT equals to minus 2VT times IA.
Yes. V brush.
Oh,
Oh no, you're right. No, I didn't. You're right. It is the RV which I should put that one. No, but that's a VD. RV is the voltage. No? And if I put the VDIA, it should. No, that one's the power. That one is the power. It has to be VDIA. But this one is the voltage. This is the voltage. So now let's look at it here. I want to explain how the self-excitation works. This is a very tricky machine. You have to be very careful what you are doing here. Remember, we said this is the E versus IF, right? Something like this, or it's just with this thing, right? So what is going to happen here? Let's look at this machine, how it's going to work. We start to rotate this machine, right? We start to rotate this machine, and it has a little bit of, not E, let's say this way. Phi. Actually, it was Phi versus IF, the first characteristic, and we call this one residual, right? Phi residual, right? Now, let's start to rotate this machine. There is some, we don't even have any current here, right? Here current is how much? Is 0. There is a little bit of, Phi residual. It's a little bit magnetic by itself. So what is going to happen if I rotate this machine? I'm going to have a small e here. How much is this e? The Ka times whatever is the speed I'm rotating times Phi residual, right? We know E in general is Kp omega, right? If there is no current in this circuit, no voltage, right? So there is nothing here. This one is open and you don't have any current. And just you are rotating this machine. Let's put it this way. And another P here, another breaker here. This one is open, right? We start to rotate this machine. There is a very small voltage here. Why? Because there is a very small magnetic property here, right? So what is going to happen? Now I'm going to clear this switch here. What is going to happen? So I have some voltage, 5 volt, 10 volt, something like that, right? So let's say this one is open for now. Forget this one. What is going to happen? I have a small voltage here. It's going to generate a small current, right? This current is going to generate some flux, right? So this flux is going to come help this one and increase the flux, right? If the flux is increased, the voltage generated is going to increase. This voltage going up is going to increase this current, right? This current going up is going to increase the flux, right? Increasing flux is going to increase the voltage. It's going to be a positive loop, right? It's not going to go to infinity because there is a limit here, right? At some point, you're not going to generate more voltage. It's not like I say, hey, I'm going to go to infinity. No. You're going to get to the point, the last, to the saturation point, and you're going to stop there. But, how about, let's say, put it this way. I'm going to put it, let's this winding was like this. I'm going to put it like this. This is I'm not putting RF and those like that. I put it this way, and I put a volt. If you put a voltmeter here, you can see the voltage gradually is going to increase. If you look at it, so based on how heavy is this machine, if this machine can go very fast, the voltage is going to go very fast. But if this machine is heavy, you can see the voltage is going to start from 5 volt. As soon as you close this switch, it's going to start from 5 volt, go 10, 15, 20, blah, 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 so the voltage is going to go. Now, we did this one. Let's say, and usually in the electric machine, you have these two available. So basically, you go there, you have something like this. You go to the lab here. They call this is the armature. You can put the two banana fish here. This is the RF. They put it like this, right? And they say this is a VT, for example, terminal. Now, when you're going to connect this one as a shunt, so you have to put one wire here, one wire here, one wire here, one wire here, and my load is going to be here. For example, you put your load here, right? And you connect this one here and here, right? So your circuit. Or you can put a breaker in the middle. Maybe there is a breaker is better. You know, if you have a breaker here, you put this one here, you put this one here. So now you can connect the load. Or this is exactly what you're going to see in the lab. You're going to go see this one in the lab. Now, somebody tell me, if I did this one other, what's going to happen? This is a generator. Direction is not animal, so somebody is rotating it from there.
It's going to increase the field voltage.
Field voltage? Anybody else?
Opposite to
Generate voltage opposite.
You're going wrong, right direction, but no.
Well, it's going to be like a full type factor now.
Okay, we'll talk about it. Anybody else wants to talk about it? If you connect the voltmeter over there, you're going to see 0 voltage. Why? What did I say here? When I explained this one, I said, okay, we have a small voltage here. When I close this switch, you're going to see a small current here. This small current is going to come generate a little bit flux. Add to this one, so the flux is going to go up. So basically, the loop is like this. Now I have a little bit phi, right? This phi is going to generate a little bit E, right? E is going to generate a little bit IF, right? IF is going to come help this one increase this, right? This one is going to increase this one is going to possibly look like this, right? Now let's go on. When I change this dot, what does it mean? See, flux is a vector, you know that. It is a direction. Let's say the small flux was like this. For example, what's the direction of the small flux, right? Phi residual. And I claim when we have a current here, it's going to generate another flux, right? So I said that flux comes this way and help this one, right? Now the resultant is bigger. The bigger resultant flux is going to generate bigger voltage, right? But how about if it must be this way? This one is upside down. So what's going to happen? So this one is going to be against the residual flux, right? So we have a little bit voltage here. We have a little bit flux. We have a little bit voltage here. It's going to generate a little bit current.